Hello, this is James Camp at Lee College in Baytown, Texas, and this is another in my series on how to program in C++. Today we're talking about complex types that hold more than one value at a time, arrays, vectors, and strings. Okay, so it occasionally comes up that you need to store more than one item. Okay, let's say that you have a phone number. Okay, and let's say that phone number is 51270512334. My apologies if that is actually somebody's phone number out there. I promise I just made it up. We have three parts to this. We have the area code. We have what's called the exchange, which I'm going to abbreviate EXCH. And then we have the extension, the part that belongs to that individual person. I'm going to call that the digits, okay, for lack of a better name. So if we wanted from this to output the entire phone number, we would see out area code, then a dash, then exchange, then another dash, and then the variable digits. Okay, and that would be a complete area phone number. But what if you wanted to access each digit individually? We could define variables int digit 1 equals 5, digit 2 equals 1, digit 3 equals 2, and keep going until we defined all 10 digits. And then if we wanted to print, even just the area code, we'd have to see out digit 1, digit 2, digit 3. We'd have to explicitly list each individual digit. There's no way to loop through them. There's no way to automate this process. And heck, we're using a computer. Don't we want ways to automate things? What if, as long as we're what-ifing, what if you didn't know ahead of time how many digits there would be? Or if instead of saving digits in a number, we were saving grades in a class you were taking, and you wanted to calculate your average homework grade, and so each time you run the program, actually there are more grades than there were last time, because presumably you keep doing homework and you keep getting new grades. I don't want to recompile the program every time we have a new number of grades, because we had to type, grade 1, grade 2, grade 3, grade 4. Goodness, isn't there a better way? Well, of course there is, or I wouldn't be doing this presentation. Yes, so there is a better way. And the better way is arrays. We can define an array to hold a phone number of int digits, and then we put a square bracket and tell the computer that we want 10 digits. Okay, and then we can go ahead and right away fill in all of those digits using what's called an initializer list. 5, 1, 2, let's see if I remember our phone number from the past page, 705 1 2 3 4. Okay, so that's a complete definition of an array. At this point, what the computer has done is created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 memory boxes, which hold the numbers 5, 1, 2, 7, 0, 5, 1, 2, 3, 4. But it's lumped these all together into one variable named digits. Okay, and that digits is an array. Now, you probably are thinking to yourself, well, we wanted to be able to access these individually. We haven't helped that by just lumping them all into one variable. But each individual digit is identified by an index or an offset. You count starting at the very first one being 0. You have 1, 2, 3, 4, 5, 6, 7, 8, up to the number of numbers minus 1, essentially. Okay, so if we want to find out what the fifth number, what the fifth digit in the phone number is, we can access digits at 4, because remember we start counting with 0, so the first digit is actually number 0 and the fifth digit is number 4. If we want to set the fifth digit to be equal to 2 instead of 0, which it currently is, we do that, and then the computer goes to spot 4 and puts a 2 there. Okay. We can now output, this time if we want to output the area code, we could do cout digits at 0, digits at 1, digits at 2. Okay. And you may say, well, we haven't really improved the situation much. You're still typing out each one individually. But because this index can be any integer, we now can actually loop through the whole thing. And caveat, we haven't studied loops yet, so just take my word for it that this will do what I say it will do. But if I type for int I for index equals 0, I is less than 10, because we have 0 through 9, I plus plus, because we're going to step through it one at a time, okay, C out digits at I, okay. Now I don't have to go through and type digits 1, digits 2, digits 3, digits 4. I can have the computer automate that whole process for me. And that's the real power of arrays, is that you can loop through them to do all sorts of processes on them by themselves. Okay, so let's look at a little more complicated example. I wanted to talk about the example of someone averaging their grades in a particular class. So we could define an int in, okay, and that is the number of grades, say the number of homework grades you've done so far in this class. We would, of course, want to see in so that the computer knows how many grades it needs to count. Then we'd create double grades of n. Okay. We'd leave that uninitialized because we're about to read in all the grades. Okay. Again, I've told you we'll learn about loops later, so just take my word for it that this will do what it's supposed to do. Okay. For int I equals 0, I less than n, I plus plus. At each, for each one of these I values between 0 and n, we're going to cn grades at I. Okay. And what this will do is create, let's say n is 5. It'll create 5 memory boxes, group them all under the name grades, and then we'll give them each an index 0, 1, 2, 3, 4. So then in my for loop, we'll start at int 0, we'll see in a grade, and let's say your first grade, you didn't do your homework very well the first time, was a 55.0. Your second homework grade, you overcompensated for that, so you got a 98.9. Then you slacked off a little bit, 77.7. Then you did really, really well, 95.4. Then you got kind of a halfway there grade, 88.8. Okay. Not a bad grade, really. I mean, it's still a B. But so we've now filled out this grades. Now, we'll learn to write functions later in the class. But let's say I've written a function called average. So I'm going to say double average grade equals, I'm going to say that I wrote a function called average, and it takes an array of grades and a number of grades to average. Okay, and it returns my average grade. And then I can see out the average of your grades is average grade. Forgot to put that in quotes. Okay. So you see here a few powerful features of arrays. We can define exactly how many need to be in the array during runtime as long as it doesn't change. We can access those elements one at a time using indexes. We can pass the entire array to an averaging function later on in the program. So some fun things you can do with arrays. Okay, downsides of arrays. Arrays are not perfect, especially the way they're implemented in C and C++. They have a fixed size. You cannot add or delete elements once the array is created. So if I create a 5-grade array and then later on I realize that I had a 6th grade that I needed to enter, I can't change it at that point. I have to quit the program, start all over again. Very inconvenient. So I either have to know ahead of time exactly how big the array needs to be, or I need to make the array overly large to leave room for expansion later. They don't know how big they are. You notice in my previous example of passing an array to a function, I had to call average of grades, and then I had to also pass in. Okay, I had to pass in here because the array grades does not know how many grades it has in it, and so the function average wouldn't know just from looking at grades how many grades there are. You have to pass the in along with it. And one big disadvantage to arrays is they can only be set all at once at initialization time. That is, I can say double grades 3 equals 75.0, 88.8, 95.5. But I can't then later say grades equals 3 new numbers. Okay, that won't compile. For this reason, I almost never use arrays in C++ anymore. I always use vectors when I'm using C++. They're called something different in different C family languages. There's the list in C#, there's the array list in Java, but it's called a vector in C++. So to use a vector, you have to first pound include the vector library, and then you have to, using namespace standard again, okay, because all of these belong to the standard namespace. Once we've done that, we can create a new type called vector angle bracket and whatever type you want to fill your vector with. It could be int or double, and we call this grades v for grades made of a vector, just to differentiate it. We can leave it uninitialized, or we can initialize it with an initialization list in parentheses. So 70.0, 88.8, 99.5. Okay. I can also initialize it with a to have all the same. So if I wanted 10 average grades, and I define an average grade as a 75, then I tell it to put 10 grades in and to make them all 75. Now, what you can do, you can still say grades v at 3, well, no, I don't have 4 elements. Grades v at 2 equals 100.0, and it'll find my, so this first statement here creates 3 memory boxes, fills them up with 70.0, 88.8, 99.5. This one finds spot 2 and refills it with 100.0. Okay, so you could do that with an array though. What you can do that's different here is you can now say grades v equals average grades, and it will actually copy those 10 75s into grades v, and it'll wipe out everything we had there to begin with and fill it up with 10 black boxes, each holding a value of 75. Okay, and then if I don't like that anymore, I can say grades v equals 55.0, 67.6, 75.5, 88.8, 95.0. I can use another initializer list here, and I can fill up grades v again, and once again wipes out everything that I have there and puts 5 new memory boxes and fills them up with 55.0, 67.6, 75.5, 88.8, 95.0. Okay. So you can see you can do a lot more with vectors as far as giving them values than you can with arrays. Okay, there are more things grades can, more things vectors can do. So I can say int num grades equals grades v dot size. Okay, now this is a important point. Vectors, unlike arrays, are objects. Okay, an object holds data, but it also has what we call methods, things that can operate on that data. Size is a method. And the way you call a method is you call its object, put a dot, and then call the method like it's a normal function with parentheses after it. So grades v dot size calls the method that figures out how big grades v is. Some other methods, I can call grades v dot insert. Let's say I want to insert at position 2, that is the third spot. So I can go grades v dot begin plus 2, and then I can insert the grade 45.6. Really bad homework grade that I made that time. If I want to add just to the end, I can do grades v dot push underscore back. That is, it's pushing something onto the back of the array, and then I got a perfect score on that homework. And maybe there's one that I don't like having anymore. I made a mistake or something, so I can grades v dot erase, grades v dot begin plus 3, and that will remove one from my array. And finally, this time, if I want to call my average function, I can send grades v by itself, and I don't have to. So I can say double my average equals average of grades v, and I don't have to tell it how many grades I have because the average function can call grades v dot size and get that number for itself. So those are some of the cool things you can do with vectors. Now, the last type I want to introduce you to today is the string type, which we've been using since the beginning of this class, but we haven't formally introduced the type or explained how it works. But before I can introduce a string, I have to introduce what a string is made of, which are characters. In C++, there is a type char, short for character, and you can use it just like any other type. Character, input, then you can cin input, and you can say, if input is y, then I'll do whatever yes would mean, and if input is no, in, I will do whatever no would mean. Okay, so what is a char? What is a character? What this char input line here does is it creates a memory box like all type character name input, like all variable declarations, it creates a little named memory box. What it holds, as far as the programmer sees, is it holds a single keyboard character. Okay, any anything you can type on your keyboard is a character. So let's say the capital letter Y, if I was trying to type yes. But what it actually holds is a numerical code, say 62. And what that numerical code represents is a letter or a number or a symbol, but it represents it as a text object. Now, in the original form of C++, characters all had 128 possible values. And those 128 possible values were governed by something called the American Standard Code for Information Interchange. I typoed there. That should be interchange. And that's ASCII for short, or ASCII is the way we pronounce it. This was one of a number of competing standards back in the day, but it kind of won out. All PCs in the 1980s used ASCII or some extended form of ASCII. And as you can see, decimal codes up to 127 defined a whole lot of different characters. The first 31 were what we call control characters. That is, these were used back in the day when a printer connected to your computer literally took a string of characters and just printed them out. So you might have you would have one control character that indicated a carriage feed or carriage return, and that control character would make the printer advance one line on its printing. There's also a line feed, which might have a different behavior. There's a horizontal tab, and there's even somewhere in here there used to be a vertical tab. I don't see it. Okay. No, there it is. Vertical tab number 11. Okay. So you could move your printing vertically in addition to horizontally. There's a bell character. So if you're working with a terminal window, you can send a bell signal and it'll go bing. And then there are other things that for transmission of text, there's a start of heading, start of text, end of transmission. All sorts of these things have to do with controlling printers or controlling terminals or controlling transmissions between computers. Starting at block 32, however, we have printable characters. So there's a space character and then a whole lot of other random keyboard symbols. Starting at number 48, we have the number 0. Starting at value 64, value 65, we have the letter A, and hexadecimal 20 plus that, which is decimal 97, we have the lowercase a, so that A and A line up, B and B line up, C and C line up, etc. So our number 62 that we entered over here is actually a greater than symbol. So if I printed this to the console, if I did cout input, it would print on the console a greater than symbol. Okay. If I had typed the capital letter Y I had used earlier as an example, that would be symbol 89. Okay. Now, at some point, it was realized that, pretty early on, I suspect, that 127 characters, 128 characters, was not really going to be enough to hold all the things you needed to express with text. For example, if you were entering the name of someone you know whose name is in German and it has an umlaut character, or you have a friend whose name is in Spanish and they have an ñ in their name, you know, that really hampers data entry and data storage if you can't represent those characters. So it was realized that a whole byte, okay, a byte actually holds, so this memory box we had created over here, 1 byte holds 256 possibilities, not 128. So you could extend ASCII with 128 additional characters. And that led to a whole bunch of different extended ASCII character sets. The IBM PC extended ASCII with, at least in the US, with character drawing symbols so that you could draw little boxes on your computer screen and then print your output in the middle of a box. You can argue whether this was useful or not. It certainly was the standard in computer interface display for a very long time on IBM PC computers. The Apple Macintosh, however, did not have text-based displays. It actually drew boxes on the screen and drew your text in as a graphic itself. So it didn't need all of those drawing characters. So Apple made their extended ASCII have lots of European characters, in with a tilde, U with an umlaut, the German long S sound. They added some mathematical symbols like pi and the partial derivative symbol and the square root symbol. So there were all sorts of things in the Apple extended ASCII that were quite useful for expressing international and mathematical concepts, but they weren't compatible between the IBM version and the Apple version. If you took a text file that had been written on a Mac and you ported it over to an IBM, a US IBM, you'd get a bunch of weird drawing characters. You know, instead of an N with a tilde that you had put in the person's name, you'd end up with a weird drawing character instead. So that didn't work very well. And to make matters worse, users of IBM compatible PCs in Europe started making their own extended ASCIIs that had the German characters or the Spanish characters. And so when the world of the internet exploded in the mid-1990s, there were all of these competing character sets out there, all of which used 1 byte to express all of their text. And we haven't even thought about the problem of expressing text from alphabets that don't use the Roman alphabet. Russian or Greek or Hebrew or Arabic all use different alphabets. So a group of programmers and computer makers and such got together and decided that it was time to scrap ASCII and come up with a completely new standard for representing text using, gasp, 2 bytes at a time. Actually, the possibility of more than that. But a 2-byte code can get you 32,000 characters, not just 256. And this new standard called Unicode can represent your standard Roman alphabet with a whole bunch of additional accented and specialized characters there. It can add Greek and Cyrillic Russian characters. It can add Hebrew and Arabic characters, the whole Hebrew and Arabic alphabets, including all of the different variants of each one. That Arabic letters are different at the start of a word and the end of a word. And it can include all sorts of mathematical and currency symbols and arrows pointing this way and that. And so there's a huge number of symbols you can now store in 2-byte Unicode. This creates a problem, however, for C++ and standard C, which were written back in the day when a character was only 1 byte. The solution that they've adopted, and I'm not sure I like it, is that the type character still refers to a 256-digit alphabet, the whatever form of extended ASCII you're using here, and W character refers to a wide character, a 2-byte character, something that can hold a Unicode value. This makes C and C++ distinctly incompatible with Java and C#, because in Java and C#, which were created after the Unicode revolution, car is by default a Unicode symbol. Okay. Why do I bring this up? Because strings, the text strings that we've been using all throughout the class so far, are essentially vectors of type character. So if I create a variable string first name equals Ralph, then what I've essentially done is create a series of memory boxes, each of which hold 1 character. Okay, so Ralph takes up 5 characters, so I have 5 memory boxes in this string, and each one is stored as an independent character. Now, the whole thing is lumped together as a type string, which is kind of similar to, but not quite identical to, a vector of characters. As we'll see on the next screen, there are some things that strings can do that vector of character can't do. If I wanted to store a person's name in some non-Western alphabet, let's say I wanted to say first name equals Ari in Hebrew, I can't do that with a C++ string, because string is limited to 256 characters, to 1 byte. So I can use a W string, which sets up here, each one of these boxes is of type character. Okay, this sets up wide characters and puts in the aleph, the resh, and the yod. Okay, so this is a wide character, a wide character, and a wide character. They behave, and they're a type W string with the name first name. For all of the examples in this class, we're assuming that you speak English or some easy to transliterate European dialect, and that you can get along with just the standard string. But all of the methods that work for string work also for W string. So if you do want to say shalom to your Hebrew friend or das vidanya to your Russian friend, you can use W strings. Okay. One other thing I want to point out while we're on this little topic is that you'll notice that when I wrote Ralph, I put it in double quotes, but when I put each character in, I put them in single quotes. C++ distinguishes two kinds of text. There are strings and there are characters. Characters always get a single quote. Strings always get a double quote. If I put quote R with double quotes, C++ is actually going to create a string type entity with just the letter R. If I put single quote R, C++ is going to create a character type entity with just the letter R. Okay. As the way in which strings are similar to vectors of type character, you can get first name dot size to get the length of the string. Because a lot of people think of strings as having a length rather than a size, which you think of an array or a vector as having a size. There's an alias to this. You can call first name dot length. Okay, and these will give you exactly the same answer. You can do dot pushback to add a character to the end of your string. So if I want to add a comma at the end of my string, I could do that. You can have dot insert to insert a character at any point in the string, and you can have dot erase to erase the characters at any point, a character at any point in your string. Okay. So those work essentially like the operators in vector, in a vector of characters. However, strings can do some things vectors can't. The first thing they can do, which we've already seen, is that you can use cin directly to populate a string. My string first name can come right in from cin, and similarly you can use cout with one or more strings. First name, if I also had a going to use a space character And if I also had a last name, I could put that there, and I can directly see out those strings. Another thing you can do with strings that you can't do with vectors is you can add them. So I can create a new string whole name. I can use the equals operator with a string. I can do that within a vector too, but a little bit differently. But I can say first name plus string space plus last name, and that is valid C++ code, even though you couldn't do that with any kind of array. You can also have string name equals Jose, and then I can type name plus equals Cuervo. Okay, so I've got all of my I've got a lot of operators that I can use with strings that I couldn't use with vectors. Finally, strings allow conversion to non-strings. So I could create string phone number equals 512123456 Okay. I have to erase these dashes for this to work, so I'm going to just not put them in the first place. 512123456 and if I want to now manipulate that as a number, I can do int S2I phone number. Forgot to name my int. Int pnum equals S2I of phone number. Okay. You can also do S2F to create a floating point number, or S2D to create a double. And you can go the other direction if you have double grade equals 98.9, and you're so proud of that you want to save it as a string, you can then say string my grade equals 2_string grade. Okay. So all of these types that I've talked about are available for, the documentation is available online at c++.com. And I encourage you to look through that and see all of the more interesting, even more interesting things you can do with vectors and strings. All right, that's it for now. Thank you for watching.